So I have 8 o'clock on the network. I don't know how accurate that is. Okay, a few items here. Normally I would send out email messages regarding this. For example, I made a mistake yesterday. Normally I'd send out an email message, but because these videos are going to be used by the distance learning students next quarter, we need to handle this stuff in class. So this was a really stupid mistake, and I'm really disappointed in myself, but it's not unusual. The hot wire microphone, the acoustic wave comes by. The acoustic wave has flow. It has particle velocity. That flow over the hot wire cools it, right? So here's the hot wire. When it's going this way, it cools it, and when it's going that way, it cools it. It actually measures twice the frequency of the actual sound wave. It's cooling this way and that way. The fact that the temperature in the sound wave is negligible here. It's negligible. So I screwed up. This is not. It's not the temperature of sound wave. It's picking up on the flow. The notes actually say it's acoustic part. It's transducing particle velocity. That's what it's transducing. And what people say is that it picks up on that. All transducer people say that. In fact, I heard it on BBC yesterday, the radio. They were interviewing a Nobel laureate, one of the two guys who first detected the cosmic microwave background. Penzias and Wilson were the two guys that do this famous story. Great transducer story now that I think about it. Although I'm not, these are microwaves, and I'm not real knowledgeable about that. But he used the same language. He says, we're picking up on this. So this is what the technical term is. It's transducing the flow here, not the temperature in the sound wave. Okay, I was wrong about that. Another thing is Kevin, look, this came up yesterday, and God, the jargon here is horrible. Yeah. Excess velocity gauge. So what are they talking about? Well, I'm going to pursue this. I'm going to try to find, I got to get that Physics Today article because they'll explain the physics. Excess velocity gauge. There's something else. Let's see. The blast wave gauge compares the speed of sound and the speed of the nuclear blast wave. What do you think they're talking about there? Okay, the speed of sound here is going to be the linear speed of, I think. This is my interpretation of this, okay? That's why I need to get the Physics Today article. The speed of sound here is the linear speed of sound. Remember, we derived it last quarter. A blast wave, particularly coming from an atomic explosion, if you're not extremely far away, it's going to be a high amplitude shock wave. Do you think it's going to travel at the speed of sound? It's going to travel faster. There's a big abrupt change in pressure, particle velocity, and temperature. So that's going to lift the speed of sound. The speed of sound of the blast wave is going to be greater, and it's probably a lot greater here. But I don't know. So I think that's what they're talking. This excess here is the speed of the blast wave beyond. And I don't think this is some special transducer. It looks to me like a loudspeaker. So whoever wrote this probably didn't know what was going on here. You got to be careful of that, right? Or they lifted it off some report and they missed some of the essential physics, right? So I think that's what's going on here. But this looks an awful lot like a loudspeaker. And I don't know the scale, we don't know the scale here, but I imagine it's a pretty big loudspeaker. Okay, so thanks, Kevin. Yeah, thank you. Any quick questions about that? Faisal, I need to talk to you after. You do have a class after this class. You all do, right? Okay, I'm still trying to get you. First week. Yeah, so I got a note here. Okay. All right, so I think I have this already. All right, so let's finish the chapter 1 today, and then we'll get into the first couple of problems in the problem set. Where we left this off yesterday was, remember there's this peculiarity here that this mechanical system here, these are all in parallel, the mechanical elements, corresponds to an electrical equivalent electrical, there's an equivalent electrical circuit where all the analogous electrical elements are in series. And now we can see, we have an indication of why that is. It's because the impedance analogy, where force is analogous to voltage, or corresponds to voltage, which is very physical, right? There's a problem here. These are actually, can be classified as different variables. This is a through variable, this is an across variable. So that's why we're having this problem here. And, excuse me, it works the other way too. So a parallel mechanical system here corresponds to a series electrical equivalent circuit. A series mechanical system will correspond to a parallel electric circuit. It works both ways, which is not surprising. Let me give you an example of that. So an example, oh, incidentally, this is not a big deal, but, okay, so here's an example. What I was just going to say, I'll incorporate it in here. Here's an example. And this is actually kind of practical interest, mainly in educational laboratories, teaching laboratories. Sometimes it's hard to put in a direct force on a mass. In the world of transducers, it's not that hard. But for an educational laboratory, you're doing some kind of mechanics, and you've got some kind of cart or a glider on an air track or something, and you want to exert a force on it. That can be hard to do. Think about it. You got this rolling. How do you do that? An oscillatory force, for example. Well, a trick here is that you can drive the boundary. That is, in some sense, equivalent to putting a force on. You have to be careful about that. Okay, it's not going to be. I doubt if it's exactly equivalent to exerting a force on here. But you can do this, and you can see, and you physically can feel this, right? And it's going to resonate. Right? Now, so the problem is, though, this is not identical to the standard case. You can see at a glance. Here's the standard thing that you did in 3119, right? So a natural question is, how do we handle this? And one of the things I want to tell you here is that it's not a big deal, but typically in a case like this, the displacement is specified here, which means the velocity is specified. And then you want to find the force on the mass. That's typically. So it's kind of a different perspective here. I mentioned this in the notes, but again, it's no big deal. But it'll kind of come up in a few minutes here. The problem is to determine the required force to give this, whatever this displacement, specified displacement, and therefore specified velocity. Incidentally, here's a little quiz, question. A force is going to be required to achieve a specified velocity here. What's this force compared to this force? There's going to be a force of this massless rigid rod here on the mass. What's the relationship between the force required to give this a certain displacement and that? Yeah, this is going to take so.
Two elements have no mass.
Yes.
Then the force
just gets transmitted. That's exactly right. And you can see, it's not real obvious. You have to stop and think about it. Okay? And this is why we use equivalent. This is part of why we use equivalent. Here, the same voltage is on each, okay? That's the analogy of the fact that the force gets transmitted through here. So essentially, there's the same force on here. If you take, the net force is 0, but if we look at the force of this side on that, it just gets transmitted through here to there, which is not, you have to think about that. But you don't have to think about this. It's the same voltage across each. Okay, that's why, it's part of why transducer people love equivalence, can't live without equivalent circuits. And that's true, as you will see in this course. Okay, so what's the equivalent circuit? I want to understand this. What's the equivalent circuit? Well, how many velocities do we have here? We've got a velocity here. We've got the velocity here will be different than this in general because the spring is going to be moving. And then we have a velocity here, and because of the action of the dashpot, we have 3 velocities. So it looks like, and this is going to be edited, okay? It looks like we should have 3 loops. It looks like we should have this, because we have 1, 2, 3 currents, right? So you say, well, we're done. There's a bit of a problem here, though. And I didn't realize this until I was looking over the notes last night. But look at this situation. Let's see, we've got a resistor. It doesn't matter how I'm doing this. Look at this circuit. How many currents do we have? Well, you know, you can say that we have 1 here. There are 3 different currents here. Now, this current's the sum of those 2, but still we have 3 different currents. So I don't think this is a rigorous argument here. I don't think this is enough. So, however, we need to do something else to nail it down. One of the things you can do, as we'll discuss later in the problem set later, is you can look at special cases where an element here is 0 or infinity. That will quickly tell you, incidentally, that that's incorrect. It does not correspond to this. Another thing we can do is we can look at force and voltage, like we were just talking about, right? It's because this force is transmitted here, and this is commented on down here. I have to edit. This really needs work. I'll do that. As we were just discussing, because the force is transmitted here, there's essentially the same force on each of these elements. That corresponds to the same voltage. So that nails it down. This is not right. This is not right. Doesn't really show up there. Okay. So this is the equivalent circuit. And you'll see here that, like we suspected, a series mechanical system corresponds to a parallel electrical circuit. We can also, I want to just mention here, that we can analytically verify that these are equivalent. You just go through here and you use Newton's laws to come up with the equation of the motion here. You use Kirchhoff's laws to come up with the equation here. Now, equation for what? Well, the perspective here, again, the typical perspective is this is a specified variable, the motion here, rather than the force. So the equation is going to be the equation for the force here and for the voltage here. All right? That's the perspective we usually have for this case like this. So here are the results. I'll discuss this a little bit once I present them to you. But here's, when you do this, when you do the Newtonian analysis, this is what you get. And when you do the Kirchhoff analysis, this is what you get for the voltage, okay? In terms of, and we're thinking of this in terms of the specified velocity here and current here. And those are equivalent. I need to add a statement here. These are equivalent. You can just see at a glance, right? Because what does the compliance, mechanical compliance correspond to? Corresponds to the frequency. Force corresponds to voltage. Resistance, the resistances correspond, and the mass. So by the impedance analogy, these two, again, to a mathematician, they're identical. Right? Even though there's a world of difference between these two, physical difference. If you tried to do this, you know, again, think lower division, you know, physics teaching laboratory. I want to set this up. And this is a circuit. There's a world of difference experimentally between the two. But mathematically, they're identical. The systems are identical. These two equations are identical through the impedance analogy. Now, I'm not going to go through this, but I invite you to do it. And how do you come up with this? Well, you got to do a Newtonian. You do a Newtonian analysis. You don't have to do that, but that's what we're doing here. You have to look at the force on here. You have to, there's some displacement here, which is going to be specified by this velocity. What's the displacement here? You don't know the displacement. There's going to be some displacement of velocity. That's an unknown. And similarly here. So you're going to introduce those two unknowns, and then you got to get rid of them. because in the end you just want one equation for the requisite force here in terms of the velocity. So you just have to go through that and be careful and look at the net force on an object. You know, you have to be careful in the application of Newton's laws. It takes effort. Every time I do it, I usually do it once a year. I have to admit this time I didn't do it. But I always have to stop and think about this, right, to get it. On the other hand, how much do we have to think about this? Okay, I have the same voltage here, right? So I write down what we know. You've all been through this, you know, in similar situations, perhaps not this identical one. This should go away, shouldn't it? Go away. I have to do this. Why isn't that? God, Adobe. Can't live without them though, can we? All right, so here it is. It's just embedded in here. We know that there's the same voltage across each. The total current, which is actually what's specified here, is the sum of the currents, okay? And we know that the potential difference across each element is the same, so we write down, we have these equations. We have a lot of equations here. You know, this is not one equation. There's several, you know, more than one equation here. So you can very easily eliminate, when you eliminate these currents here, okay, for example, the current through the capacitor is going to be, you know, omega times the charge. Okay, you can eliminate this, and similarly you can eliminate this current. Okay, what you end up with is this. You can almost do it in your head. So this is expressing a fact. This is the current through the capacitor. This is the current through the resistor. This is the current through the inductor. And you can see the use, and we're going to get into the use of impedance here very quickly. You see it coming, right? What's the impedance of a capacitor? I omega C, right? So 1 over I omega C. The impedance of the resistor is R. So this is the impedance sitting down here. Now we haven't introduced that yet. This is still introductory, but we're going to be using, and we did a lot of this last quarter, but we're doing a lot of it this quarter too. Okay. This last sentence is not, I don't think, I'm going to omit this. It's true, it's not wrong, but I just don't think it's worth putting in there. Okay, so we got into this because of, to point out the fact that because our impedance analogy is mixed between through and across variables, this is why that's happening. And it happens both ways. You know, series here corresponds to parallel. Parallel here corresponds to series here. So the lesson here, and if it will really sink in, we're going to do it explicitly. We will eventually do it in a problem set. I don't know when. We're going to actually go through the calculations. But if you're interested, as I said to you, you can go through the analysis. You can derive this. You'll find it's a lot more work than coming up with this. And that's the big lesson here that all transducer people know. It's equivalent circuit is much, unless it's a very simple system, the equivalent circuit is much easier to solve in the mechanical system. This happens again and again in the transducer world. Okay. Any questions? So there is this other analogy. All right. And somewhere in the notes it's mentioned when it was, it may have been in use before it was published, but it wasn't until 1933, which, you know, okay, I don't know the history of the analogy, but I don't know, that seems kind of late to me, I think. And it's very reasonable that it would be late because the impedance analogy is so simple, and we think that that's the only one, but it's not. There are probably others too. But the only one's going to concern us. And I have to tell you, it's only going to concern us a little bit, so don't think that if you don't feel comfortable with this, don't think it's the end of the world, okay? We're not going to, we're only going to use this in one or maybe two cases, I can't remember, right? So it's called the mobility analogy. And here, it's not mixed. The through variable of force here corresponds to the through variable of current here. Now, I don't have any physical feel for force corresponding to current, all right? But mathematically, it's entirely permissible. And going along with that, velocity on a cross variable corresponds to voltage. So that forces some of the other things here. The displacement here, the time integral of this will correspond to the time integral. This has no name as far as I know. The time integral of the force will correspond to the time integral of the current. And there is a name for this. It's in mechanics. It's the impulse. A lot of times, particularly in collisions, the details of the force are often can be very complicated and fortunately are not really important. What's important is the impulse, if you may remember from mechanics. So that actually has a name. And the integral of this has a name. The current has a name. It's the electric charge, okay? So that they correspond. And I guess I have to say it turns out, and we'll indirectly verify this in a moment, the mass corresponds to the capacitance here. The mechanical resistance corresponds to the inverse electrical resistance, which is called the conductance. And finally, the compliance here corresponds to the inductance. That's annoying. I thought they were supposed to be done by now. Have you guys heard anything about that?
I heard March.
Another quarter? God. And I have to tell you, when you guys go back in there, you guys use that, right? I hardly ever go in there. It's probably not going to be very different. Putting all this money and all this time and all this noise to renovate that building. We went through that in this building before you guys came here. Like 3 years ago, Gene, when was it? I don't know. 3 or 4 years ago, this building was renovated. It took forever. And, we now have tile in the bathrooms. Great. We really need that, right? So, anyway. But you're used to this, right? The federal government, right? Yeah, you know how this works. Okay. It's like that jargon, excess velocity transducer or whatever they said. This is like good jargon, right? It's like part of the federal government. Okay. Okay, so why are we going to use this? I can't tell you we can't get into that right now why we're going to use it. But you can see one advantage of the mobility analogy. What do you think the equivalent circuit's going to look like for this? It's all going to be in series, right? And we can verify that. And we can do it in a kind of indirect way. So see if you can follow this. It's not that complicated, but it's a different perspective. Let's consider this series mechanical system, okay? We suspect that the equivalent circuit will be all be series. All right. So let's see. How did I do? We know what the equation we've established, although I actually just stated it. This is how that mechanical system obeys. Okay, this is the force has to obey this. This is how you find the force. You solve this equation. Okay, let's go in there and make the mobility correspondence. Okay, so you remember what does this correspond to? What's the mechanical compliance? I've already forgotten. Whatever it is.
Inductance.
Right, thank you. There it is. Okay, let's go through and make those replacements. I think I've actually might have written them down here. Yeah. So the force corresponds to the current. Go through there, make all those the correspondences. Here's what you get. Okay, now I don't know if that looks familiar to you, but if you go back, we actually did consider this circuit before. It's right here. If you look at this, so that what's supposed to happen here is that if you look, it's on the next page, the equation here, this should be equivalent to, when you go through and make this, should be equivalent to that. Okay? Now, the reason I'm hesitating here is it's not important, but it's this perspective on what is specified and what needs to be solved for. And I guess I didn't realize that until right now. There's a little bit of a problem here because we think typically of this as being specified, and therefore this should be specified. But if you look at the equation that we've got here, it's okay. It's mathematically equivalent. Yeah, it's fine. So here's the point. Here's what we just did. And I don't know if it's worth saving the time because we're spending more time than we might be saving. Okay? But instead of just looking at this problem, saying, okay, what is the equivalent circuit of this in the mobility analogy? Instead of doing that, what we've done is we've got the equation for the mechanical circuit. We've made the correspondence in here. We come up with an equation, and we find that that equation is identical to the equation that we already knew for the pure series circuit. Here it is. We already knew what that is. So that verifies all this, that what corresponds to the series mechanical circuit or system is what corresponds to that is the series electrical circuit. Okay, and again, we'll only need this one or two cases. You don't really need to worry about it. But it's interesting. It is interesting that you're not locked in on just one analogy here for electrical and mechanical systems, even though this one is not very physical. But it will have a use. We'll get at least one usage out of it. Does anybody have any questions? Okay, so what we want to do now is, I better bring this up. So I need to talk to you a little bit. I'll zoom in on this later. So this is the document that you should. It's on Sakai. You maybe have printed it out or got a digital copy or downloaded it. You'll notice something here. There's a problem. Brian's book has problems in the back of the chapter. There aren't that many problems. But some of the problems are problematic. They need further specification or something. It varies. It's not a lot of them, but some of them are I don't know how else to say it. They're problematic. I can't say that they're a problem because they already are a problem because they're okay. But there's a problem with the problem. Okay. So typically when that happens, it doesn't happen often in a textbook. When it does, the instructor will just find another problem to assign. That's a sound problem. That's another word people use, sound, but it's not a good word to use in this course, right? Because we use sound differently. So I don't know how to say it. It's problematic. So coupled with the fact that I've also introduced other things, like the lock-in amplifier, a number of the problem sets will have these lettered problems. This is the ones that I've come up with, okay? Sometimes, look here, it's just, that's it. These are evidently not very simple problems, just two problems, right? So that's how we're going to handle this. There'll be the numbered problems from the book. Here's just part A, and then the lettered problems, okay? All right. So we're going to look, it's appropriate, I think, now to look, we're going to look at the 2 lettered number problems for the first problem set. And then tomorrow we'll do the problems that are assigned from the textbook. So let me fix this here. Okay, so the first, maybe I should have, okay, so the first problem here has to do with a lock-in amplifier. And the whole idea here is that in our probe, the resistive probe, we can't do a DC measurement because of electrolysis. So we put a carrier, a high frequency carrier on there, okay? Frequency omega naught. But then, so that'll allow us, any chemical changes there will be reversing. So they won't be permanent. That won't cause a big change in sensitivity or erode one of the wires, which, as I told you guys, can actually happen. That was in water, incidentally. The demonstration you saw was in alcohol, so I don't know what will happen in alcohol, but it doesn't matter. You just don't, if you don't have to deal with problems like that, you move on, right? You don't deal with them. So we just drive it with a high frequency, much higher than the wave frequency that we're trying to measure. Now, I just edited the notes on this, which you'll get the lecture notes. Yeah, so you'll get the edited lecture notes very soon. Okay, and there'll be our procedure here is to replace the notes on Sakai with the edited notes, right? You guys know that? Okay. I didn't explain this phase factor in the lecture notes, and I should have. But here's the idea. Our reference signal, let's take it to be a pure cosine. So that's the modulation, right? The carrier. Not the modulation, it's the carrier. Okay, at this relatively high frequency. How does the probe respond? The probe is in there in the water. And you can forget the fact that there's a surface wave, just assume it's equilibrium. How's the probe going to respond? What do you think to this? You think Ohm's law? So how's it going to respond? Just set F equal to a constant here. That's just no wave, just ambient. How do you think, what signal are we going to get when we look across the probe? We'd expect it to be in phase because it's purely resistive, right? Transducer people don't assume that, and there's a good reason why. Okay, so for example, could there be some capacitance between those two wires? Yep. What's that going to do to the response? It's going to introduce a phase. Okay? There's another reason, though, why we want to be general about this. The transducer is not just those two wires. It's all the electronics that's used to support that sensor. And there can be capacitance and inductance. You know, if you're dealing with a sensitive system, you may have to worry about cable, the B and C cable, the capacitance in the cables there. Well, actually, that'll come up in a problem later on in the course. So we want to be general here. This is a sort of a standard approach, and you'll start to see it next week when we get into the next chapter. So we want to be general here. We got to put this phase in here, and we don't know what that is. So if you look at what's in the notes, we went through, and we looked. A lock-in actually converts the signal here at omega naught down to DC, and then bandpass, and then does a low-pass filter. But the way I presented the notes, just to get the feeling for what's going on, is we did this averaging, right? So if you look back in the notes, what we did was we multiplied the signal that we're getting by cosine omega naught t, and we showed, you can go back and look at this, when you do the time average, you just get this. And then we said, oh, we've got our F. This is what we're after, the F. we've got our f. And I think I pointed out to you in the lecture is, well, what about, how do we handle this cosine of phi? We don't really have f, okay, this little f, because we don't know what the cosine of phi is. So, in lock-in language, this quantity, the component of this is the, so like the component of the signal, or the in, also called the, it's in phase with the reference, or the carrier, is called capital X. That's universal lock-in language. That's why I'm doing it here. So this has nothing to do with, you don't want to think reactance here, okay, like we sometimes do with X. We have X and R. In lock-in language, it's different, okay? So this is the in-phase, it's called the in-phase component, all right? The way we can get rid of this is, to take a wild guess, is we also look at the 90 degrees out of phase component. That's called the quadrature component. So in lock-in language, it's called Y. This is the quadrature. And there we multiply f by the sine of omega naught t. And I'll leave it to you. It's very simple. If you go back and look at this derivation, going from here to here, you'll see that you get, it carries over. If you replace the cosine here with a sine, all you got to do is replace the cosine there with a sine. You should verify that. Okay? So now we've got these 2 bits of information here. We have this in-phase information and the quadrature information. And from that, you can see we can solve for f here. If I take x squared and add it to y squared and take the square root, that's called R in lock-in capital R in lock-in language. I get this. Now to be precise here, when I take that square root, technically there could be a plus or minus sign here, right? When I square this and add it to the square of that and recognize that the phase goes away, when I take that square root, there could be a plus or minus sign. Almost always this is irrelevant. This 180 degrees phase shift here is irrelevant. But if you want to know what it is, you can get it. You can actually, I think the standard way to do this is, you'll notice if we take, instead of squaring and adding these, if we take the ratio of x to y, we eliminate f here, and we solve for the phase. So this is the phase in terms of the in-phase and quadrature components right here. This looks like circular logic. I'm having trouble with this. Oh.
And the signs of y and x tell you what quadrant the phasing was in?
Right. So you can do it any way you want to. Once you know what this is, if you look here, for example, once you know what phi is, and we're really just after the sign here, you can then from here, you should be able to. I'm having trouble with this. You should be able to nail down that sign. I'm having a little trouble with this, but it's first of all, I want to make sure you realize it's almost nobody usually cares about that plus or minus, but you can nail it down if you want to. I will look at this again, and I'm already going to edit. I'm going to edit it anyway. I have already some editing. Okay. So as with the lecture notes, that's going to be reposted and emailed to you. But I'll wait till after tomorrow when we do the other problems, the other solutions in here. Okay? I'll look at this again. But it's no big deal, but you can do it. You can nail it down. And incidentally, just in case you ever have to use a lock-in, it's in the history of lock-ins. In the beginning, I guess, they didn't do both of these, but modern lock-ins are called technically dual phase lock-ins. And what that dual phase means, it finds X and Y. It finds all this stuff for you. So that lock-in that I was using for the surface wave demonstration, I was using R. I didn't care about this phase. And I just punched it in. I just dealt with the buttons and the lock-in. It'll give you, the dual phase refers to the in-phase and quadrature components, the X and the Y. That's what it refers to. And I think in the beginning there were lock-ins that just had one, they were actually single phase. They just did one of the phases. I don't think you can find those anymore. Incidentally, I don't know if I told you guys, but people are still interested in lock-in amplifiers. You should, okay? I told you, I gave you a reason, I gave you one example of why they can be very useful, right? When we talked about it. I see them advertised in Physics Today, right? Not only that, this may come as a big surprise to you. They advertise analog lock-ins. So years ago, when lock-ins finally went fully digital, it was great, because in the analog days, you'd have to really know what you're doing with a lock-in amplifier to get the right answer. Digital lock-in amplifiers are very forgiving. If you get an answer, it's probably the right one. So you can be real lazy. I'm real lazy. That's a fully digital lock-in amplifier, that one that we were using. I'm real lazy with that. I just start punching, and once I get something that looks right, I know from experience that it's going to be right. I shouldn't admit this, but you know, it's human nature, I guess. But with an analog lock-in, and when I was a graduate student, that's all that they had. You had to really know what you were doing. But analog lock-ins are now being advertised in Physics Today. So what do you conclude? What do you think? What do you think is going on there? Again, lock-in amplifiers dig signal out of noise very accurately, right? Why do you think they're advertising analog amplifiers? What do you think? That's what I would think. That there are people doing, you know, detecting these very small signals, and due to digitization, there's noise there. Interesting, huh? Okay, any questions? I'll look into this again, and I'll fix this up. This statement here. I think this is right, but I'll check into it. Okay, the next problem is an equivalent circuit problem. And the problem is, find the equivalent electrical circuit for this mechanical system. This is not the same as, you know, it looks different, right? It's not the same as that other series circuit that we dealt with in lecture notes. So how do we do this? Well, the first thing is, this is what I do, and I recommend it. Is you look at, because it's the easiest thing, is to look at the count the velocities. Well, there's this all has one velocity here, right? And there's a velocity here. There are just two velocities. So our equivalent electrical circuit, whatever it may be, has got to have what? Two loops. And we don't run into this the more complicated situation we did with two loops. You gotta. So here's what I do actually when I'm trying to come up with an equivalent circuit. And I recognize, okay, in this case, we've got to have two loops. So, so I usually draw in light lines. I draw this, okay? And I draw it in light lines because I'm going to be putting elements in here, right? It's got to have that kind of structure. So we've already made some progress. Now the next issue is, where do we put the electrical, you know, we know this is going to correspond to a mass. This is going to correspond to an inductor. Oh, I'm sorry. This is wow. Okay. Oh, is that the way I did these when I did these notes? Oh God. Oh, I know the problem here is that, right, if you make this look like a, yeah, there's a problem. This is just a notational. You know, often we think of this as a spring, right? Well, it also looks like a resistor, doesn't it? So you're kind of screwed which either way, however you do it here. So we want to recognize this is mechanical. This is a spring. Okay? So this will correspond to a capacitor, an inductor, and an electrical resistor. So what's left is we've got to decide where to put them here. And How do you do it? Well, notice something here. This has a velocity, right, which will correspond to a current. The velocity here is the same. Now, when we talk about a velocity of a spring, remember what we're really saying is it's really the difference, but this is anchored down. So the fact that these have the same velocity means the electrical equivalents have to have the same current, right? So what do I do here? Well, I put these here, and of course it doesn't matter where we put them. It nails it down. Now you might say, well, wait a minute, what if you put something here? Why is that obviously incorrect? So why can't the resistor go here? Well, then what are we going to have over here? A short. Obviously not right? So that means these won't be doing anything. So that actually uniquely nails it down. This is how it works, okay? It's interesting. And again, I think it would be a great proving ground for artificial intelligence because it requires some kind of thought. There's no like clear-cut procedure here. You have to sort of think about it, right? And in a kind of creative way, more than just a clear-cut, algorithm like type thing. So that nails it down. It's got to look like this. Now, if you're still concerned, we can do some checks. One of them is it's sort of a general thing. The force here, this is a massless element. So the force here is equal and opposite to the force. There can be no net force on this. The force just gets transmitted through here. So the force on here is going to be the same as the force on this combination, which means the voltages have to be the same. The voltage across this has to be the same as the voltage across that. So that helps. That's confirmation, right? Another thing you can do is you can go through special cases. Now, this is kind of painful here. We're not going to go through all these, but you can go through all of them. If you have any question, you can always talk to me, right? How many special cases do we have here? And by special cases, I mean, zero capacitance, infinite capacitance, etc. There's going to be 6 possibilities. So I went through them all here, and it's painful. Every time I do this, it's painful to go through these, but let's just go through a couple here, just so you get the idea. If this is indeed the equivalent electrical circuit, it has to hold in the limit as the capacitance goes to 0. What happens as the capacitance goes to 0? What do we end up with? Q is equal to CV. We've got C going to 0. It's actually good to take the time derivative here. It means no current. So if I have no current going through here, what do I have? I have an open switch. It's open. It's very useful. In this course, it's useful to think in that limit, because we always want to look in limiting cases. Sometimes you have a limiting case in a physical system, and it's good to be aware of it because it can simplify things. Here we're doing it just to check. If this really is the equivalent circuit, it's got to hold in the limit where we just have an open switch there. When we have an open switch, what happens? There's no current through there. Okay. So what does that mean regarding the mass? It's not going to be moving. Okay. So and also the spring. So let's check that. Let's go up here. If we set the compliance equal to 0, this is where you have to think a little bit. What does 0 compliance mean? It's not, that's right, it's not compliant at all. So this becomes a massless rod. What's going to happen to M? So it doesn't move. Does M move? No. Okay, check mark. And I'm going to edit the check marks to make everyone, including me, feel better. I should have a check mark here. So it checks in that case. All right? We can look at the other limiting case. What is infinite capacitance? A short, right? So it's like a closed switch. It's acting like a closed switch. In that case, the voltage across the inductor and the resistor are the same. So that means that there has to be the same force on the mass and the dash pot. Okay? So when we have the open switch, we have infinite what does infinite compliance mean?
Zero stiffness.
Right. So it's like we cut this. We've removed it. We cut it or remove it. And in that case, there is going to be the same. You don't have to worry about the force of the spring anymore. And the force, this force gets transmitted, there's the same force. So check mark. Okay, so I invite you to go, you can go through this. And I've seen transducer people do this. I've done this before. People seldom go through all the special checks, okay? But if you really are concerned, you can. It gets kind of tedious here, but you can. Usually I just do one or two, just a couple of checks just to make sure. But it helps you believe, it helps you believe the system, that you got the right answer. So that's the idea there. Okay, does anybody have any questions? So tomorrow, the first thing we'll do is we'll do the numbered problems. This is from the back of the chapter in Brian's book. And then we'll start to get into the next chapter, which will amaze you. I was amazed. There's like a general theoretical approach to transduction, which is really interesting. And not trivial, but I'll guide you through it. Okay.